The evolution of urban mobility systems is explored, showcasing how innovative engineering is shaping the cities of tomorrow. Viewers are taken on a journey through the cutting-edge technologies poised to redefine how people move within metropolitan areas. Imagine a city where traffic jams are a distant memory and your daily commute feels like something out of a sci-fi movie. What if I told you that future is closer than you think, being built right now by brilliant engineers? This video explores the mind-bending innovations poised to revolutionize how we navigate our urban landscapes. Tired of endless commutes and gridlocked streets? Our cities are bursting at the seams, and traditional transportation simply can't keep up. But what if there was a radical new approach, designed to move millions seamlessly and sustainably? Get ready to discover the groundbreaking engineering solutions transforming urban mobility as we speak. Picture this: flying taxis silently gliding through skyscrapers, underground hyperloops whisking you across town in minutes, and intelligent networks predicting your every move. This isn't just a fantasy, it's the meticulous work of engineers pushing the boundaries of urban transportation. Join us as we unveil the incredible technologies shaping the cities of tomorrow. The global urban mobility crisis, characterized by worsening traffic congestion, air pollution, and inefficient transit, is a complex challenge driven by rapid urbanization and heavy reliance on private vehicles. The crisis has severe economic, environmental, and social consequences, prompting cities worldwide to seek sustainable and integrated solutions. Traffic congestion reduces average travel speeds, especially during peak hours. In cities like Kolkata, average peak hour speeds can drop to just 10 km per hour, wasting time and energy for commuters. In many cities, public transportation and road infrastructure, built for smaller populations, are now overwhelmed. This has been exacerbated by the explosive growth in private vehicle ownership in the absence of robust public transit systems. Congestion leads to higher vehicle emissions, contributing significantly to urban air pollution. In Delhi, for example, vehicle emissions account for 30% of particulate pollution. Stop-and-go traffic increases fuel consumption and emissions, hindering efforts to combat climate change. To address these pervasive issues, cities are implementing multifaceted solutions that focus on integrated planning, technology, and behavioral change. Establishing unified metropolitan transport authorities can improve coordination among various agencies, ensuring that transport and land use planning are aligned to create more livable and efficient cities. Traditional urban movement solutions, built around the private automobile and expansion of roads, are failing to keep pace with rapid urbanization because they create a self-defeating cycle of congestion, environmental damage, and inequity. Cities worldwide are struggling under the pressure of soaring populations and vehicle ownership, highlighting the urgent need for a radical rethinking of urban mobility. Electric vertical takeoff and landing (eVTOL), aircraft and air taxis are poised to disrupt traditional commutes by enabling urban air mobility (UAM), a new category of on-demand air transportation. These flying vehicles promise to ease urban congestion, reduce travel times, and provide a quieter, more environmentally friendly alternative to ground transportation. However, significant technological, regulatory, and infrastructural challenges must be addressed before widespread adoption. By leveraging underused low-altitude airspace, eVTOLs can bypass the gridlock that chokes city streets during rush hour. A daily commute that currently takes hours could be completed in minutes. eVTOLs can land on rooftops, parks, or designated vertiports, allowing access to locations that are difficult to reach with existing transportation infrastructure. This would enhance connectivity between different urban hubs, such as business districts and airports. Unlike traditional transportation hubs that require large, centralized airports, a network of smaller vertiports throughout a city would offer a decentralized model of transit. This would give commuters more options for origin and destination points. Running on electric power, eVTOLs produce zero in-flight carbon emissions, leading to improved air quality in dense urban areas. They are also significantly quieter than conventional helicopters, reducing noise pollution. Autonomous capabilities are a key part of the UAM vision. Advancements in artificial intelligence (AI) and machine learning (ML) are enabling advanced navigation and autonomous flight, which would eventually remove the need for onboard pilots. While some initial commercial services and pilot projects are expected to launch in a few cities by 2025 to 2026, widespread adoption will be a more gradual process. Overcoming the identified hurdles will require ongoing collaboration between manufacturers, regulators, infrastructure developers, and urban planners. As technology matures and costs decrease, UAM could eventually become a significant part of the urban transportation ecosystem. A Hyperloop system is an ultra-high-speed transport concept using pressurized pods traveling through partially evacuated tubes, combining the speed of air travel with the convenience of ground transportation. An integrated public transport system uses smart routing and autonomous pods. Hyperloop systems, ultra-high-speed underground travel to minimize air resistance. Hyperloop pods travel inside sealed, partially evacuated tubes. Reduced drag allows for high speeds with minimal energy consumption. The pods use contactless propulsion and magnetic levitation, maglev, to glide silently and with minimal friction. This technology is similar to that of advanced maglev trains, but with the benefit of a near-vacuum environment to achieve much higher velocities. Proposed speeds range from 600 to over 700 miles per hour, about 1,000 to 1,200 kilometers per hour, with test pods already reaching speeds of nearly 300 miles per hour in competitions. Travel times between major cities could be drastically reduced, such as Mumbai to Pune in 25 minutes. Hyperloop tubes can be built above ground on columns or, for urban areas, below ground in tunnels to minimize disruption. Several companies, such as Transpod and Heart Hyperloop, are actively developing the technology, with test tracks and facilities constructed globally. India, through a collaboration between IIT Madras and Indian Railways, has invested in a 422-meter test track and is planning a commercial project. Maintaining a stable, long-distance vacuum and compensating for thermal expansion in large tubes remain significant engineering challenges. The initial capital investment for infrastructure is immense, and developers must address potential safety concerns related to high speed, emergency evacuation, and security. Fleets of shared, electric autonomous pods use AI and real-time data to operate on demand, without a human driver. Some concepts propose pods that can link together like a train during peak hours and separate during off-peak times. While Hyperloop is focused on ultra-high-speed, intercity travel, integrated autonomous pods offer a flexible and dynamic solution for urban and last-mile transport. Combined, these systems could form a seamless network. Implementation requires significant investment in supporting technology and infrastructure, as well as coordination between operators and proactive government policies. As a new technology, regulatory and safety standards are still being developed, and public skepticism about self-driving vehicles remains a hurdle. Smart infrastructure uses AI and predictive analytics to create intelligent, responsive traffic management systems. By analyzing vast amounts of real-time and historical data, these brains behind the flow can optimize traffic signals, predict congestion, and enhance overall mobility and safety. Smart infrastructure uses a network of sensors and data sources to gain a real-time picture of traffic conditions and predict future events. Devices embedded in roads and mounted on intersections collect real-time data on vehicle speed, count, and density. Computer vision algorithms analyze video feeds to classify vehicles, monitor lane occupancy, and detect incidents. By combining massive datasets from various sources, these systems identify the causes of congestion and inform decision-making in real time. This technique allows traffic signal systems to learn optimal green light timing by continuously evaluating the effect of its actions on overall traffic flow. Traditional traffic lights run on fixed timers. AI-powered signals adapt dynamically based on real-time traffic volume, pedestrian activity, and incidents. This reduces wait times and keeps traffic flowing. Cities like Phoenix and Pittsburgh have seen significant reductions in vehicle delay and travel times by implementing such systems. Sensor networks and real-time data are transforming urban planning by creating dynamic, data-driven systems, which is especially critical for integrating and managing electric vehicle (EV) fleets with energy grids. The two concepts are mutually reinforcing, as the data collected informs urban policy. Urban areas are becoming smarter by leveraging sensor networks, the Internet of Things, IoT, to gather and analyze real-time data on various aspects of city life. This dynamic data flow allows city officials to move away from slow, static planning processes toward a responsive, adaptive approach. The electrification of urban transport places significant new demands on a city's energy infrastructure. Smart grid technology, supported by real-time data, is essential for managing the integration of EV fleets without overwhelming the power grid. Integrating on-site renewable sources, such as solar panels, and battery energy storage systems, BESS, can reduce a fleet's dependence on the main power grid. An energy management system, EMS, can help manage these assets along with the EV charging load. Personalized mobility and on-demand autonomous ride-sharing represent a paradigm shift in urban transport, moving toward a future where travel is safer, more efficient, and tailored to individual needs. This model, known as Autonomous Mobility on Demand, AMOV, uses fleets of self-driving electric vehicles managed by a central system to meet traveler requests via mobile applications. Legal and ethical questions remain, particularly concerning liability in the event of an accident. Regulations must be standardized and harmonized across different jurisdictions. Advanced e-bikes and scooters are leading the micromobility revolution, offering efficient, flexible, and sustainable urban transport solutions. These advanced vehicles, combined with user-friendly subscription models, are providing seamless access to diverse transport options and are projected to reach a global market value of around $340 billion by 2030. Modern vehicles include advanced safety measures such as anti-lock braking systems, ABS, built-in sensors for sidewalk detection, and AI-powered voice alerts to improve rider safety and prevent accidents. Improvements in ergonomics and design make these vehicles more comfortable and practical, with features like ergonomic seating, smart displays, and built-in charging ports. Part of a broader trend toward mobility as a service, MaaS, some subscription plans bundle micromobility access with other public transport options like buses and trains for an integrated travel experience. Next-generation transport is redefining cities through technology, sustainability, and human-centric design, shifting urban planning away from car-dominated models. Instead of building around private vehicles, cities are being redesigned to prioritize people, improve quality of life, and increase accessibility through integrated, multimodal networks. By dramatically shortening travel times between cities, Hyperloop could expand economic zones and allow people to live farther from city centers without the burden of a long commute. By offering a fast, sustainable, and high-capacity alternative to planes and traditional trains, Hyperloop could alleviate pressure on existing transport networks and reduce emissions from long distance. Hyper-efficient cities, or smart cities, leverage a network of connected technologies, data, and intelligent infrastructure to optimize urban functions and dramatically improve the quality of life. This integrated approach addresses pressing urban challenges like congestion, pollution, and resource consumption, creating a more sustainable, prosperous, and responsive urban environment. Real-time environmental sensors monitor air and water quality, allowing cities to mitigate pollution and reduce related health issues. Smart healthcare initiatives, like remote patient monitoring, can also help manage chronic conditions and reduce hospital readmissions. Your day begins with a hyper-efficient journey. Smart traffic management systems use real-time data to adjust traffic signals dynamically, eliminating bottlenecks. Autonomous public transit, from buses to light rail, is perfectly synchronized to minimize wait times, and mobile apps give you real-time updates on arrival and occupancy. If you drive, an app directs you to the fastest route and even reserves an available parking spot for you near your destination.